So what we trying to do in this talk is we try to understand a new technique to find what we call eigenvectors. The traditional methods takes about 5 steps, but in our methods we will see that we only need 2 steps. So the whole talk is about how to develop the theory and how to achieve what we want to do. So we're going to say finding eigenvectors, fast and non-traditional approach. So let's see a little bit of things that we're going to discuss in here. So we're going to talk about the historical development and then also some related definitions before we move on. And then also we can talk about the naming convention, because we already know that we have 2 things, what we call the eigenvector and the eigenvalue. And then we're going to introduce a new concepts called Eigenmatrix here. And then also we can talk about related results, some of the major results, and then how we can use these ideas in classroom. Because we know that when we try to teach these things in classroom, for example, in a class like called a differential equation, or linear algebra, or PC analysis in computer science, or robotics in engineering. So there are a lot of application things that they use eigenvectors. So maybe this is useful for any of those classes. And also starting this semester, we're gonna start teaching this method. Actually, start next week for our linear algebra classes for the first time. So let's talk about a little bit of theories. So we know Daniel Bernoulli. So Daniel Bernoulli is the one who came up with the background of the eigenvector. And we also know Daniel Bernoulli is the one who came up with what we normally call the Bernoulli principle in physics, or this is the one they govern the planes, or maybe how a bird fly. And also in historical days, they use Bernoulli principle to find the blood pressure. They kind of use a glass tube and poke into your veins and see how far the blood goes, and from that you can see what's the pressure. So it's a kind of thing they did in a long time. But right now, fortunately, we have new techniques these days. And then the related work, for example, where these eigenvectors coming from, he had a nice experimental work about vibrating strings. And when you talk about the theory for vibrating strings, what happened? They came up with what we call a configuration. So this is the Daniel Bernoulli's principle, actual experiment, and this is so we got those from his own work. So these are robes. So they use kind of robes to develop what they call the configurations. And these days we know that these configurations are the eigenvectors. So these are the eigenvectors for certain eigenvalues. So he had some kind of idea behind the eigenvectors in those days, but not the way we know right now. But the actual birthplace is his work. And then let's try to understand what is a linear system. So what's a linear system? Let's say you have a problem. You go to a bakery and then you try to order a cake. So I'm going to say, okay, give me a cake. And then once I say give me a cake, what's going to happen? The baker is going to give you a lot of options. So these are all the options that the baker is going to give you. Now the question is, so this is like you are writing an equation with several variables. So different type of cakes, you have several variables. Now let's say you're going to make it kind of restrict. So let's say I'm going to say, okay, no, give me a birthday cake. So now what happened is it's the same system, but now you're going to add one more constraint to it. So you're going to get what we call birthday cake. So that means you add one more restriction. You're going to restrict your solution set to a smaller one. But that's not the actual case. So what are you going to do? You're going to add one more restriction. Let's say you're going to see, oh no, give me a cake for my daughter. So so that means you add one more equation. That means you adding one more restriction. So what's going to happen? You're going to get what you call your unique solution. So and that is like you kind of building a system of equations. So that means let's look at the real theory behind. So that means you're going to say, okay, give me a cake. So that means you're going to write your first equation. And then what you're going to say, you're going to get a lot of solutions. There are a lot of unnecessary solutions there. So what you're going to do, you're going to restrict it. How to restrict? You're going to put one more, you're going to post one more condition. You're going to say, okay, I need a birthday cake. That means you're going to add one more condition there. Once you add one more condition, it's going to cut off the solution set to a smaller one. And then you also say, no, I need a cake for my daughter. So that means you're going to add one more condition. So that means it's going to slow down, it's going to bring, in certain situations, a unique solution. So not always, but it can bring a unique solution. And then also we had a question like, what is, like we know that there are some systems. This is what we normally call a linear system. So you have a linear system. Now we know that when you talk about linear algebra, we know that there are situations where there are no solution situations. So how you can interpret that in a real life situation? For example, let's say you're going to go to a baker and then you're going to say, I need a cake, but the cake worth let's say $14.99, but you only have $10. So that means you cannot buy that. So that is the kind of situation. There's a no solution situation. So you can kind of bring those things together and come up with real nice situations there, just to explain things to your students. So yeah. So then so what we have right now is what we call a linear system. Now let's look at and then what we normally do is in linear algebra, we're going to look at the coefficients. We can look at just the coefficient 1, 3/2, 1, and then we have one constant there, and we have 0, 3, -2, and then 1, 0, 1/2. What we normally do is we can write that system as what we call a system of equations. So this is what we do in linear algebra. We write the coefficient there, we put the variables there, that's the constant. We can write this system as just one equation, what we call Ax equal b. So we still don't see any eigenvectors here so far. So let's see where those eigenvectors coming from. For example, we have what we call the double pendulum problem. So this is like something appears in like a modeling problems. So let's look at what we call the double pendulum problem. So what's going to happen in a double pendulum problem? So you're going to see there are two bobs, and then with some rod attached into it, and it's going to go in a random motion, and not really random because this is deterministic, but you can see it's really chaotic motion. Okay, so now the thing is that how to develop the theories for double pendulum problems, and then we know that if you look at the governing equation, the governing equation you can write it in this form. So this is what we discuss normally in dynamical system classes or differential equation classes. You can write the motion as a differential equation. So and then how to solve it? So when you solve it, this is the equation that you get. So you can see the angle that the bob gonna make with the vertical line can be given as this equation. So this is the solution for that. And then you can see there are two special vectors sitting there, and those are the eigenvectors corresponding to the system. So that's where the eigenvector comes to a situation where you're going to solve a differential equation problem, and that's why those are important. And but when you talk about the dynamical systems, we normally call those modes. We don't call it eigenvectors, vectors. We normally call those modes. So that's the kind of terminology that we use there. Okay, so let's look at some related definitions before we move on. So, what is an eigenvalue? An eigenvector. So let A be an n by n matrix. The roots of the characteristic equation, which is the determinant of A minus lambda equals 0, are called the eigenvalues of A. And then if you can find a non-zero nu such that A minus lambda I times nu equals 0, we call that is the eigenvector corresponding to the eigenvalue lambda. So normally eigenvalue and the eigenvector go as a pair. So we call eigenvalue eigenvector pair. And then there's what we call eigenspace. So what's the eigenspace? And you know that this is like a simple solving a system of equation situation. So that means this system have solutions, and we know that V equals 0 is always a solution, but there can be more. There can be more solutions. And if you consider all such solutions, we call this is the eigenspace of the lambda. Okay, it's eigenspace of lambda. and the number of base elements. So because this is a space, subspace of Zn, so that means this may have a basis, and the number of base elements is called the geometric multiplicity of lambda. The number of basis elements of this space is called the geometric multiplicity of lambda. So let's look at a situation how we actually find this in a real situation.
How to solve.
So this is Dr. Gilbert Strand trying to explain how to solve the problem.
Ax equal lambda x when we got two unknowns both in the equation. Okay, here's the trick. Simple idea. Bring this onto the same side. Rewrite. Bring this over as A minus lambda times the identity x equals 0, right? I have Ax minus lambda x. So I brought that over and I've got 0 left on the right-hand side. Okay. I don't know lambda and I don't know x, but I do know something here. What I know is if I'm going to be able to solve this thing, for some x that's not the 0 vector, that's a useless eigenvector, doesn't count. What I know now is that this matrix must be what? If I'm going to be able, if there is an x, I don't care if right now I don't know what it is. I'm going to find lambda first, actually. But if there is an x, it tells me that this matrix, this special combination, which is like the matrix A with lambda shifted by lambda I, that it has to be singular. This matrix must be singular, otherwise the only x would be the 0x and 0 interest. Okay, so this is singular. And what do I now know about singular matrices? Their determinant is 0. So from the fact that that has to be singular, I know that the determinant of A minus lambda I has to be 0. And that, now I've got x out of it. I've got an equation for lambda, the key equation. It's called the characteristic equation, or the eigenvalue equation. And that, in other words, I'm now in a position to find lambda first. So this is the idea will be to find lambda first. And actually, I won't find one lambda. I'll find n different lambdas. Well, n lambdas, maybe not n different ones. A lambda could be repeated. A repeated lambda is the source of all trouble in 1806. So let's hope for the moment that they're not repeated. They were different, right? 1 and minus 1 for that permutation. Okay, so, and after I found this lambda, can I just look ahead? How am I going to find x? After I have found this lambda, the lambda being one of the numbers that makes this matrix singular, then, of course, finding x is just by elimination, right? It's just, now I've got a singular matrix. I'm looking for the null space. We're experts at finding the null space. You know, you do elimination, you identify the pivot columns and so on, and give values to the free variables. Probably there will only be one free variable. We'll give it the value 1, like there, and we find the other variable. You can get the half of this, or you can multiply this one by 2. So it's up to you how you're going to do it. And you can see that's what you get. Now you can see this is the exact same equation, and that should happen. We know that when you try to find eigenvectors, that is the case. It should be the case. It should be
the case that these two are equal. And then what you do, you're going to pick one of the equation and you try to solve for one of the variable. It doesn't really matter which one. You still get the same answer at the end. So what he did, he solved for x1 in terms of x2. And then what you can do is, you just need like a one special value. Just pick some values there. Don't put 0, but pick something else. And then you're going to get the eigenvector as x1, x2. Or you can write as a row vector, or you can write this as a column vector if you want. It's just how you're going to represent that. So in this case, 1, 2. Now, we do the same thing with the other lambda value. So we can do lambda equal -1, and then let's see how we're going to finish the problem. So once you finish the the other steps, and then you can see that you get the other eigen vector like that. So this is the eigenvector for lambda equal 3, and that is the eigenvector for lambda equal -1. And then, so these are the kind of steps that we normally do use to solve such a problem. So we can find the eigenvalues, and then we're going to find what we call the we can plug in the values there and then simplify, and then we do the row reduction, and then after the row reduction we going to write the corresponding system, and then we're going to solve for basic variables in terms of free variables, and then we write the vector, and then once you write the vector in the parametric vector form, and then you get the eigenvector. So there are 1, 2, 3, 4, 5 steps for such a problem. And then how about a matrix like a 4 by 4 matrix? So let's say this matrix has 2 eigenvalues, lambda 1 equal 2 with multiplicity 1, and lambda 1 equal lambda 2 equal 1 with multiplicity 3. You can see that for just a 2 by 2 matrix, it took like kind of about 5-6 minutes. How about a 4 by 4? It might take a long time, because especially when you do the row reduction. How about a 5 by 5? Maybe with fractions. So this one has again 2 eigenvalues, lambda 1 equal 1 with multiplicity 4, and then lambda 2 equal -1 with multiplicity 1. But don't worry, we can solve this problem at the end. It probably take like 30 seconds. Okay, but if you want to do this problem, it's going to take about 20 to 40 minutes in a standard way. So now this is what we did not see so far. So what we did not see, you can see that this is the eigenvector for lambda 1 equal 3. But you can see this eigenvector is sitting there in this matrix. See, you can see 1, 2 is already there. It's there. So that means all those steps are not necessary, because you can see just subtract, eigenvector is there. And if you look at the other one, for example, if you see eigenvector for lambda 2 equal -1, you can see it is 1, -2. It is already sitting there. This is 1, -2. So that means all these other steps are not necessary, because the eigenvector, that one is sitting there, eigenvector, this is sitting there. So also you can see multiple of that. For example, this is also eigenvector for lambda 1 equal 3, and also this is an eigenvector for lambda 2 equal -1. So what's our argument is, all the rest of the steps are not necessary, because the eigenvector is only simply sitting there in there. So that's what we're gonna kind of explain in this rest of the talk. So we have like a shortcut for 2 by 2. For example, if A is a 2 by 2 matrix, we do not need this the traditional way to find the eigenvectors, because for example, if you have A equal A, B, C, D, 2 by 2 matrix with distinct eigenvalues lambda 1 and lambda 2, and then what we can show is that if you just subtract the eigenvalue, we normally what we call the complementary eigenvalue. You have to subtract the other eigenvalue. If you subtract the complementary eigenvalue from the diagonal entry, then it's going to be a eigenvector for lambda 1. So similarly, if to find the eigenvector for lambda 2, what do? You subtract lambda 1 from the diagonal entry of the other one. So remember, you have to subtract from diagonal entry. And it is interesting to see that you can actually subtract from any diagonal. It doesn't really matter which one, unless you get a 0. If you get a 0, you have to skip that and find something else. So you pick a column vector and subtract the complementary eigenvalue from the diagonal entry. It's going to produce the eigenvector. So in this case, if you put in a summary, so let's say your eigenvalues are lambda 1 and lambda 2. To find the eigenvector for lambda 1, you're going to subtract lambda 2 from that first column. To find the eigenvector for lambda 2, you subtract lambda 1 from the second column. So that is the eigenvector for lambda 1, and this is the eigenvector for lambda 2. And then we also know that there are some small related theories, and then any non-zero multiple of eigenvector is still eigenvector. And then what we normally do is we can scale them by removing extra negative signs or fractions just to make it easy, so that it's easy to work with. And then also there is no distinction between real and complex eigen values. It still works. And then also one of the interesting things is that the eigenvalues appear in a reverse order. So you have to switch the two, because it's always you subtract the complementary eigenvalue. So this is the eigenvector for lambda 1. This is the eigenvector for lambda 2. And you can see that you can even subtract from the same column. Still going to produce the eigenvectors. So this is one of the interesting things here. Now, let's see why this works. For example, for a 2x2 general matrix, so we know that that's a characteristic equation. So this is what we normally call the trace and the determinant. And then you can find the eigen values using the quadratic equation. So once you plug in that to the quadratic equation, this is what you get. And then you know that that's the trace, and then plus or minus, this is trace a squared, and then the 4 times the determinant. And then you can also simplify this slightly like that. And then what happened, lambda 1, lambda 2 product is the determinant, and the lambda 1 plus lambda 2 is the trace. Now let's see how we're going to do the calculation. Let's say lambda 1 is the corresponding eigen vector, but we know that, so this is the A minus lambda 1 I matrix, and that's the corresponding eigenvector. This is you get by subtracting lambda 2 here. And then you're going to multiply through. Once you multiply through, what's going to happen? We substitute for lambda 1, lambda 2, that one, A plus D, and then lambda 1, lambda 2 is the determinant. Once you plug in that there, you can see it simplifies very well, and you get 0. And also you can see if you substitute for this one as lambda 1 plus lambda 2 is A plus D, you can see it simplifies and gets 0. So that means it works, because we need to check whether when you multiply with a vector, you get 0. Yes, you get 0. And also you know that this is not equal to 0. We assume that. So that means, yes, this is an eigenvector. So this is a proof for a 2x2 case. And then let's try to talk about new theories that we develop throughout this research. We define what we call a kappa matrix or the eigenmatrix. So what is that? Let A be an n by n matrix, and you pick a lambda from the spectrum, and then we call the matrix given by A minus lambda. This is your familiar matrix that we have to deal with, but we're going to call this is the eigenmatrix. The reason is it's going to produce the eigenvectors or the characteristic matrix. And then since we say it's a characteristic matrix, to sound right, we're going to use the kappa because of the characteristic sound. So, we're going to call it the kappa lambda A. That is the same matrix. We're going to call it the kappa matrix, or we're going to call it kappa matrix, or what we can call it eigenmatrix. So that's a new term introduced to mathematics, just to follow with the eigenvalue and eigenvector concept. So then the determinant of a kappa matrix is the characteristic polynomial. We normally use that rho A or P A lambda. So it's just up to you how we write it, but we can call it P. Okay, the matrix produced is not commutative. We know that if you do the matrix product, it is not commutative. But the interesting thing is that if you multiply two kappa matrices, they're going to be that product is commutative. So the product of kappa matrix is commutative for a given matrix A, and it's very easy to see. If you have two matrices for two different eigenvalues, and you can see that's what you get, but you can see this is commutative and that's commutative. That means the product has to be commutative, and we're going to use that fact later. Okay. So let's talk about the rationale behind picking the naming terminology for that. We know that we use normally lambda and mu for eigenvalues, and then we use nu for eigenvectors. And then, so the question is, what is the best choice? What's the best choice for a eigenmatrix? So the best choice for an eigenmatrix would be something closer. So we're going to pick the letter preceding lambda. So that means it is a kappa. So that means according to the Greek alphabet, we have kappa, lambda, mu, nu in that order. So we can use the kappa for eigenmatrix. We use lambda, mu for eigenvalues, and then we use nu for eigenvector. So they are nicely aligned in that order. So it's a coincidence, but it works very well. Good. And then we need one more result from regular linear algebra, and we call what is a diagonalization theorem. Diagonalization theorem. So that means if you have a matrix, you can transform that to a diagonal matrix. And how to do it? You're going to multiply by a special matrix. So what we normally call the transformation matrix. So what it says, an n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. So if n has n, remember it has to match n and n. So if it has n linearly independent eigenvectors, then you can diagonalize the matrix. And then the sum of the dimensions of the eigen spaces equals n. So that's one of the conditions. So that means the sum of the dimension of the eigenspaces should be equal to n. So under those conditions, we can diagonalize a given matrix. So let's talk about another new result that we developed. So what we call the two-spectrum lemma. So what's a two-spectrum lemma is about? Let's say you are given a n by n diagonalizable matrix A, which has spectrum 2. That means there are two different eigenvalues. So we're going to call it lambda 1 and lambda 2 being the two eigenvalues. Then what's going to happen? If you calculate those two kappa matrices and if you multiply them, you can see that the product is going to be 0. That's amazing. So you're going to get a 0 product when you multiply those two kappa matrices. And that's the key result why we can find the eigenvectors the way we find it. Because you can see that the product is 0, you can consider these are columns. So that means you can see if you pick this column is a vector, what's going to happen? You multiply this matrix with one of the vector and it's equal to 0. In other words, that's an eigenvector of lambda 1. And then, so you can see you can pick any column here, just pick any column and then you see when you multiply you get 0. So that means any non-zero column of this is eigenvector of that. And then to see the other way around, switch the two. You can switch the two, you can put lambda 2 here, lambda 1 there, and then you can see that when you multiply vectors of this one with that, you still get 0. That means the non-zero columns of that are eigenvectors of lambda 2. So that was the idea behind. And that's the major result. So we call this is a two-spectrum lemma. And also there's another version of that, it's the same thing but you can write in a different way. So if an n by n matrix, diagonalizable matrix A has a spectrum 2, then the non-zero columns of the kappa matrices are the eigenvectors of the complementary eigenvalue. So you have to be very careful with that word because it's not the same one, it's the other eigenvalue. That's why we say complementary eigenvalue. It's the same thing written in a different form. So we call these a two-spectrum lemma because the shorter form works for when we have two eigenvalues. So it's a two-spectrum lemma. Again, as a new result. And then we have eigenmatrix lemma. So that's a general case. So what's the general case? So we call this is eigenmatrix lemma. Eigenmatrix lemma. So if lambda is an eigenvalue of A, the eigenvectors of A lies in the column space for the complementary eigenvalue. So you can see that the eigenvectors of lambda lies on the column space because you can see that the product equals 0. So that means it's in the column. So that means, and also we know that any linear combination is still eigenvector. So that means eigenvectors of lambda 1 is sitting on the column space for a complementary eigenvalue. This is not the same lambda, so this is for a different eigenvalue. So it's for a complementary eigenvalue. So that is, if mu not equal to lambda is another eigenvalue of A, the associated eigenvector of mu lies on the column space of or the null space of lambda, or the column space of A minus lambda I. So we call this is the Eigenmatrix lemma. And then so this is the geometry behind it. So you can see that so if you want to find the eigenvector for lambda 3, you know that that eigenvector sitting on the column space of lambda 2 and the column space of lambda 1. So that means it has to be in the common line. So we know that these are two planes. So there's a is cut through a line, but in general it's going to be like a space one dimension less. But here, if you see, these are two dimensional. So in the case of two dimensional, you can see they cut through a line, and so the goal is to find that common line, because we know that the eigenvector of lambda 3 sitting in this column space and that column space. So that means it has to be in the common to both. Okay, and also in so and then you can see that, so if you have three such eigen column spaces, and then there's a common point and the 0 vector is sitting there, and then so that's the eigenvector for lambda 2, that's the eigenvector for lambda 3, that's the eigenvector for lambda 1. Okay, so the column space is gonna nicely explain the theory behind the eigenvectors. Okay, so let's move on. And then we have what we call the Eigenmatrix theorem. So this is a generalization of the result. So what it says, let A be a diagonalizable matrix n by n, and then let's pick the distinct eigenvalues from 1 through p. We're going to call it lambda 1 through lambda p. And then what happens if the matrix is diagonalizable, and if these are the distinct eigenvalues, what's going to happen if you multiply them through for the distinct eigenvalues, you get a 0. You get a 0 there. And if you use the kappa matrix notation here, and then we can see that you can write this one as the kappa matrix for lambda 1. This is the kappa matrix for lambda 2. This is a kappa matrix for lambda c. So you can write the same thing using kappa matrices like that. And then in addition, so what you can do is in addition, the non-zero columns of the vectors of the matrix. So you can see when you multiply, let's say you just pull out one of them and multiply everything else. So you take out one, multiply everything. For example, you pick the kappa matrix for lambda I out, and then multiply everything else, and you can see that this can produce a single matrix. Now you can see that the non-zero columns of this matrix are the eigenvectors for lambda I. Because of this argument, because you can see, so if you need lambda I, because you know that these products are commutative, you can bring it in front and multiply everything else. So that product is going to give you that, and then it does not really matter what order you multiply here, because these are commutative, and then you can see any non-zero column of that is a eigen vector for lambda I. So it works very well, and it's not that difficult to prove. We can prove this one using what we call the Cayley-Hamilton theorem. So the Cayley-Hamilton theorem is the major tool behind this work. So we know that according to the Cayley-Hamilton theorem, so we know that the matrix A itself satisfies its own characteristic polynomial, or in this case the characteristic equation, and then we know that we can factor it. According to the fundamental theorem of linear algebra, fundamental theorem of algebra, we can factor it. And once you factor it, you can substitute for lambda, you can substitute for A, and that's where you get the result that we discussed here. So so it's simply a consequence of the Cayley-Hamilton theorem. And then we assume that these eigenvectors are distinct. But you can see in general, this can be true for not for distinct eigenvalues. Even the eigenvalue repeat, this always exists. If you consider all the eigenvalues with the multiplicity, so that means some eigenvalues may repeat, then this is always the case. So this is true always if you consider all the eigenvalues, whether they are equal or not. But when the eigenvalues are distinct, and the matrix is diagonalizable, then we're going to get this special situation. So here we don't have repeated eigenvalues. These are only the distinct eigenvalues. But if you have, for a general matrix, what's going to happen? If you consider all the eigenvalues, then this is always true. This is always true. But the problem is the column may or may not be 0, because you might get some non-zero columns for certain matrices. So then it doesn't produce eigenvectors as we are expecting. Okay, so that's about that. And then, so the quick way to find the eigenvectors, because we know that the finding eigenvector is a problem that we deal with in linear algebra classes and differential equation classes, as we discussed at the beginning of the talk. And then, so this is like kind of shortcut to use that in the classroom. After we discuss these theories behind, and then we can kind of explain the situation, because for 2 by 2, it's easy to prove the result. Just multiply 2 as we did few slides before, and you can multiply them, and then you can show that it works always. So that means we can have this shortcut formula or the quick method for 2 by 2 matrices. So let lambda 1 and lambda 2 be the distinct eigenvalues of a 2 by 2 matrix A. The eigenvectors of A can be found by columns of A by subtracting the complementary eigenvalue from the diagonal entries if the resulting columns are non-zero. So what you can do, so after you get the distinct eigenvalues, what we can do is you can simplify the eigenvectors just by subtracting the other eigenvalue from the diagonal entry. And it doesn't matter which column you pick, you can pick any column, but remember to subtract from the corresponding diagonal entry. Okay, so that's for 2 by 2. And then let's see, so let's look at a situation where how the theory works for a 2 by 2 matrix. And actually that is the problem that we kind of discovered this technique, because I gave this question as a problem in the final exam for my computational linear algebra class, and some students make mistakes, and then that mistakes forced me to find a shortcut, or like I was thinking like, why this is so difficult, and whether there is another way to do it, and that how we came up with this idea. So, and then I'm going to call it the magical problem, because that's the problem actually caused, kind of gave birth to the idea. So let's see. So we have a matrix which is A 1 2 3 4. It's kind of neat, and then we're going to do we're going to find the eigenvalues. So what you do, we're going to look at the characteristic polynomial here. So once you do it, it's 3 minus lambda, 4 minus lambda, minus 2 1. We set it equal to 0. You can simplify it. And then this has nice factors, so we're going to get 2 and 5. So we know those are distinct. Now what we normally do is we're going to write to find the eigenvectors. So for that, what we do is we can use a shortcut now. So what the shortcut is, we're going to calculate the kappa matrix for lambda equal 2, and then we also find the kappa matrix for lambda equal 5. So those are the kappa matrices, and then we know that now. These are the eigenvectors for lambda equal 5. These are the eigenvectors for lambda equal 2 from the shortcut. Okay, so that means so we have those two now, and then by the shortcut, now what we're trying to do is we're going to diagonalize the matrix. We're going to put the eigenvalues first. So we have the diagonal, but that's a D matrix. So we put the eigenvalues in the diagonal. So 5 and 2. Now what we're going to do to get 5. For the eigenvalues of 5 are these are the eigenvectors of 5, so we're going to put that there first, and then the eigenvectors for 2 are coming here, and here you see that they are the same, but here they are different, but it doesn't matter, just pick anything. So for example, you switch the order and put it there. So eigenvectors of 5 goes here, that's coming from here. Eigenvectors of 2, eigenvectors of 2 coming from there, you're going to put it there, and then you're going to multiply by the inverse of that. So this is the diagonalization of A, and you can see it's a diagonalize. And then we use this result. This is a common result for 2 by 2 determinants, 2 by 2 inverses. Okay, so now the question is, so it works for 2 by 2 nicely. but whether this is going to work for 3 by 3. So let's look at a problem. So for example, let's say you have a 3 by 3 matrix which has 3 eigenvalues, 0, 3, and -4, and I found it for you. So, and then as before, we're going to calculate the corresponding kappa matrices. So we have lambda 1 equal 0, lambda 2 equal 3, and lambda 3 equal -4. And then what are you going to do? You can see that none of the columns are 0. So the goal is to, we know that the eigenvector is sitting in the other column spaces, so right? So eigenvector is sitting in the complementary column spaces. So that means if you want to find the eigenvectors for lambda 3, what do? You need to find the common vector for the column space of those two. But that's not that difficult. What you normally do is, so we're going to find 2 vectors that is perpendicular to the column spaces, and then we're going to multiply those 2 vectors to produce a common vector, and that common vector is the eigenvector of that. So that's the kind of argument we do here, because we know that the eigenvector is sitting in the complementary column spaces. Okay, so eigenvector of that is sitting in the complementary column spaces. So that means so you need to find a vector that is sitting in here and also sitting in there, and then like we need to find what is common to those 2 column spaces. So this is the idea. So we're going to pick the 2 vectors. So let's say you're going to find the eigenvector for lambda 1 equals 0. What you're going to do, you're going to multiply 2 vectors. So we're going to, the normal vector to the column space of lambda 1 equals 0 is coming from how to get the normal vector for that. So we're going to pick 2 vectors and then take the cross product. That's going to produce a normal vector to the column space. So we can do that. We're going to just pick 2 vectors and take the cross product, and then it's going to produce a vector, and that's a normal vector for the column space. And we can do this. So, and then you can even escape, because you see there are 2 negative signs. So the best thing would be just multiply by negative and consider this as the eigenvector, because it's much simpler. Not the eigenvector, the normal vector. And similarly, we can find another vector for the other space. So for this one, we can do a similar argument, and we can find one for that. So, and then what's going to happen? So that normal vector is, after similar calculation, you can see it is 832. And then now what are you going to do? We're going to take the cross product of those 2 to find the common vector. So once you take the cross product of those 2, what's going to happen when you take the cross product of n1 and n2, it's going to produce that vector and then normalize. And then you're going to get that one with least number of negative signs, and then you can see this is the eigenvector for lambda 3. Okay, this is the eigenvector for lambda 3. So that means you can just use simple cross product to find the eigenvectors. This is not the normal way to do it, but it works because we know that the eigenvector is sitting in the complementary column spaces. It's sitting in the complementary column space. Okay. So in geometry, this is the idea. So what we're trying to do, we try to find the eigenvector for lambda 3. So what we're trying to do, we need to find a common vector. For that, what we do, we find the normal vector of lambda 1, of the column space of lambda 1, and the normal vector of column space of lambda 2. And then what we do, we know that we need to find a common vector to those 2 spaces, and that you can get from, if you look at the cross product of those 2, because that's parallel, and that one, and that's going to be parallel to this vector. So you can simply pick that one or any scale of that as the eigenvector. So that's the kind of idea behind the argument we discuss here. Okay, so and then also there's another argument. You can simply use the matrix product to find the eigenvectors. So for example, let's say we want to find the eigenvector for lambda 3. So what do? You're going to multiply the other 2. We're going to multiply the kappa matrices for 3 and the kappa matrices for -4. So this is kappa matrix for 3 and -4. When you multiply, this is what you get. And you can see there are some non-zero columns. So according to our argument, this is going to be a eigenvector for lambda 0, okay, or lambda 1 equals 0. That's the eigenvector. And also, and you can see that this is actually unnecessary. We don't need to multiply everything here because we are looking for just one vector. Since we are looking for just one vector, so the best thing would be just pick one column. You pick the whole matrix here and only pick, let's say, column 1. Okay, it's going to be a trial and error situation because, you know, like for example, if you pick column 2, it's going to be 0. So you have to pick something else. So just pick the first one and then multiply. And then in this case, I just pick the first column. And then when you multiply, you get something non-zero. Excellent. And that's going to be the eigenvector. So this is the kind of another way to find the eigenvectors for a eigenvalue, just by the matrix product, and you don't want to multiply everything, just multiply one of them. Okay? And if it is 0, that's the eigenvector for the other eigenvalue. So you can see, so you multiply 3 and -4, that means this is going to be eigenvector for other one, that means 0. Okay. So how about, so we waiting for this question for a long time, and remember we had a problem how to find the eigenvector for a 5 by 5 matrix, but now we know what to do. And we know that this matrix has 2 eigenvalues, lambda 1 with multiplicity 4 and the lambda 2 with multiplicity 1. So that means since this has multiplicity 4, that means you need 4 eigenvectors. Multiplicity 4 means 4 eigenvectors. How to find it? You simply subtract the other eigenvalue from the diagonal entry. Just subtract the other eigenvalue from the diagonal entry. Once you subtract from the diagonal entries, it's going to give you the eigenvectors. So let's do it. So I'm going to subtract. So here it doesn't matter. So what you want to do is you can pick any column. So it can be the first 4 column or first column, second column, third column, fourth column, whatever you like. So just think about the how you can do it faster or how you get an easy calculation. So what I normally do is, because I need 4 eigenvectors for lambda 1, so I pick the last 4 columns and then subtract -1. Subtract -1 means add 1. So you simply add 1 to the diagonal entry. So that means this is eigenvector, that's the eigenvector. Those last 4 are the eigenvectors of lambda 1 equal 1. And then lambda 2 with multiplicity 1. So you need 1 eigenvector, that means you subtract 1 from the first one. So it's going to be the eigenvector for lambda 2. And then what we can do is we can do some simplification. For example, let's look at the first column. If you look at the first column, this is what you get. So after you simplify, you're going to get these columns. You can just keep this, use this as the eigenvectors, or you can scale them. But for example, if you look at the first example, you can see 33 is common. So you can divide by 33. And also you can multiply by 64 to get a like a nicer number. So after we do something like that, removing the after we scale, so we're gonna get something like this. So you can see these numbers are not that bad. And then you end up with these matrices, and you can see if you do this problem like this way, I mean it won't take that much time. So you know, maybe less than 1 minute you can find all the eigenvectors of a 5 by 5 matrix if the matrix has 2 eigenvalues. And then so anyone has any questions? Okay, so so I'm going to let you look at this again and try to completely understand. And there is a preprint published in archive, and you can read more about that, and you can also find proof of those results there. And then also I explain, you know, we also talk about what happened, you know, the matrix is not diagonalizable. So if the matrix is not diagonalizable, what's going to happen is going to bring it to the Jordan canonical form. And there are some explanations about that also there. And there are some open problems that you may want to try. So it's going to open up a whole lot of new problems, and also like really interesting. And then the student might feel like comfortable to work with eigenvectors this way because they just use some calc 3 properties and just simple matrix products to find eigenvectors. So you can see we only need 2 steps right now rather than using 5 steps. And then I'm going to call, and then one thing we notice is you can see the eigenvector is sitting on the other column spaces. So we're going to call it, you're going to find your puppy in with the neighbors, because the puppy is the eigenvector, but the eigenvector is sitting on the other column spaces. So we're going to call the puppy, your puppy is in the neighbors, with the neighbors, because it's not with the kappa matrix of the same eigenvalue is of the kappa matrix of the other eigenvalues. So we can simply say that find your puppy with the neighbors. Okay, so thank you so much, and I hope you kind of learned something, and then we try to use them in the future studies and in the research and things like that. Thank you so much.